Hello everyone. In this pre-lecture tutorial, I want to provide a demonstration on how to calculate pH during several stages within a strong acid, strong base titration. I'll also be posting a follow-up tutorial where I do the same for a weak acid, strong base titration, and we'll have a discussion in class comparing and contrasting the two situations. But for now, I think it's important for you guys to see what these calculations look like, and so I'm going to provide this example so that you can work on the follow-up assignments and supplement your reading, and then we'll proceed from there. So here we have this example problem where I have a 30 milliliter sample of a 0.15 molar sodium hydroxide solution that I'm going to be titrating with a 0.125 molar hydrochloric acid solution. And I'm asked to calculate the pH at several different stages within the titration. I've got at 0 milliliters, so basically before I've added any acid at all, at 35 milliliters, at 36 milliliters, and also after having added 40 milliliters of the hydrochloric acid solution, which serves as the titrant for this titration. And so, in order to calculate the pH prior to adding any acid at all, then basically all I have is just 0.15 molar sodium hydroxide. And so, we've done these types of calculations before. We know that sodium hydroxide is a strong base, and so it dissociates completely to sodium ions and hydroxide ions. And if I'm going to find the pH, then what I'm going to need to do is make use of the relationship that the pH added to the pOH at 25 degrees Celsius is equal to 14. And so I'm going to need to take 14 and subtract the pOH from it. So if you recall, the pOH is the negative log of the hydroxide ion concentration. So I'm going to need this hydroxide ion concentration, and since our stoichiometry for the dissociation process is 1:1, then the starting concentration of the sodium hydroxide solution is equal to the hydroxide ion concentration. And so if I go ahead and substitute in, and then I do the math, I actually get a pH of 13.18. Okay, but how do I handle the case where I have to calculate the pH after 35 milliliters of the hydrochloric acid have been added? So here, it would help if I actually think of this process as a two-step process. The first process is basically I have the addition of the hydrochloric acid to the sodium hydroxide. Okay, and that's just a neutralization reaction. And neutralization reactions occur fully to completion. And so basically what's going to happen is I'm going to get sodium chloride and water. Now, if you recall, based on what we learned at the end of chapter 16, sodium chloride would produce sodium ions and chloride ions, but neither of those ions have any effect on the pH. And so all that's going to happen here is I'm going to be consuming some of the sodium hydroxide. And in order for me to figure out exactly what's going on, it actually ends up being a limiting reagent problem, because essentially I'm starting with 30 milliliters of 0.15 molar solution of one reagent, and in this particular instance 35 milliliters of a 0.125 molar solution of the other reagent. And so I need to solve that limiting reagent stoichiometry first before proceeding to calculate the pH. And so I'm going to go and I'm going to convert each of these concentrations to moles so that I can see which reactant is fully consumed and which reactant is in excess. And so I'm going to need to go and, since I have 30 milliliters of 0.15 molar sodium hydroxide, I'm going to convert those milliliters to liters, and I'm going to convert that concentration of sodium hydroxide to moles. That works out to 4.5 times 10 to the negative third moles of the sodium hydroxide. Okay? Now, for the hydrochloric acid, at this stage of the titration, I've added 35 milliliters, but the concentration of the hydrochloric acid, if you recall, is 0.125 molar. And so I'm going to convert that to moles of hydrochloric acid, and that ends up working out to 4.375 times 10 to the negative third moles of the hydrochloric acid. And so, since the hydrochloric acid is the limiting reagent, then basically this reaction will proceed until all of the 4.375 times 10 to the negative third moles of hydrochloric acid are consumed. Since the stoichiometry is 1 to 1, then basically what's going to happen is I'm going to be losing this same number of moles of sodium hydroxide. So if I subtract 4.5 times 10 to the negative third moles of sodium hydroxide that were initially present, if I subtract 4.375 times 10 to the negative third moles of the sodium hydroxide that will react with these 4.375 times 10 to the negative third moles of hydrochloric acid, I'll have remaining 1.25 times 10 to the negative fourth moles of the sodium hydroxide. Now, if I'm going to calculate the pH, since again I'm still dealing with a concentration of hydroxide ion, then I would still need to use this relationship, which can be rewritten using a little bit of algebra as this. Okay, but I'm not going to put the 1.25 times 10 to the negative fourth moles directly into here because, again, remember, this term in the equation should be a molar concentration. And so what I need to do is I need to divide this out by the total volume of solution once I've added the 35 milliliters of the 0.125 molar hydrochloric acid. And so that means this volume of the hydrochloric acid should be added to the initial volume of the sodium hydroxide. And if we do that, at this point in the titration, I should have 0.065 liters of solution. So I'm going to divide this number of moles by that volume. And if I do that, then I get 1.92 times 10 to the negative third molar hydroxide ion at this point in the titration. So now, if I go ahead and substitute that in and do the math, at this point in the titration, I get a pH of 11.28. Okay? Now, I'm going to repeat the same process after having added 36 milliliters of the hydrochloric acid, and let's see how that's different. Once again, I'll have to begin by calculating the number of moles of each species on the reactant side to see which of the two reactants remains. And so I'm going to go and I'm going to calculate out my number of moles of hydrochloric acid added at this point in the titration. Already having calculated the moles of sodium hydroxide, that's going to remain constant at each step of the titration in terms of the initial amount of the sodium hydroxide. So I'm going to go ahead and calculate this out, and when I do, it comes out that after adding 36 milliliters of 0.125 molar hydrochloric acid, I would have added 4.5 times 10 to the negative third moles of hydrochloric acid. So what that means, if we sort of delve into the stoichiometry of what that means, then that means that I would have completely exhausted both of my reactants. So basically, by the time that the titration reaches this point, at the end of this point of the titration, I would have no sodium hydroxide, no hydrochloric acid. And so I would have had 4.5 times 10 to the negative third moles of the sodium chloride, and also 4.5 times 10 to the negative third moles of water. Now again, sodium chloride, neither of those ions would actually contribute significant acidic or basic behavior, and that just leaves me with water in its pure state. And if you recall all the way back to the beginning of chapter 16, when we were discussing water and essentially its pH behavior, water in its pure state has a pH of 7. So what that means is, after having added 36 milliliters of this 0.125 molar hydrochloric acid, I would have added equal amounts of moles of both acid and base. That means I've reached the equivalence point of the titration. And so, at the equivalence point for a strong acid, strong base titration, the pH will be 7, because I would have achieved neutrality. Now let's go on and see what happens after having added 40 milliliters of base. So once again, I'm going to go and I'm going to calculate 40 milliliters of acid, I should say. We are adding 40 milliliters of 0.125 molar hydrochloric acid to the 30 milliliters of the 0.15 molar sodium hydroxide as a base. I'm going to go ahead and calculate the number of moles of the hydrochloric acid that result from that addition. So that would be 0.040 liters of 0.125 molar hydrochloric acid. And if I go ahead and do that calculation, I end up with 5 times 10 to the negative third moles of hydrochloric acid added at this point in the titration. If you recall, basically we started with 4.5 times 10 to the negative third moles of sodium hydroxide. And so that means that now the hydrochloric acid is in excess. So we should be expecting an acidic pH. And so if I go ahead and subtract the 4.5 times 10 to the negative third moles of the sodium hydroxide that we had initially from the 4.5 times 10 to the negative third moles of sodium hydroxide that would react, then that means that I would have 5 times 10 to the negative fourth moles of the hydrochloric acid remaining. Okay, and if I'm going to calculate the pH, then basically I should just take the negative log of the hydrogen ion concentration, but again recall this is a molar concentration. This quantity is just the number of moles of hydrochloric acid. And so I'd have to divide by the total volume of solution at this point in the titration. So that means I would have to add these 0.040 liters to the 0.030 liters of the base that were initially present. So that means I have to divide by 0.070 liters, or 70 milliliters, of solution that would be present at this point in the titration. When I go ahead and do that math, I get 0.00714 molar hydrochloric acid at this point in the titration. If I go ahead and substitute that in, then I get a pH of 2.15. And so if we actually take these pH values and actually plot them, what we'll get is a titration curve. So initially, if we compare, we had a pH of 13.18 at the start of the titration because we were titrating a certain volume of base. So that would be about here, more or less. Okay, and then after 35 milliliters, our pH was 11.28. So that would be roughly, let's see, this is 35 milliliters, 11.28 would be, say, there. All right, but at 36 milliliters, if you recall, we were already at 7. So 36 milliliters would be right next to it, and 7's here. And then after 40 milliliters, we had a pH of 2.15, which is right around here. So if we go ahead and connect those points on the curve, what we would get if we actually plotted more of the points on the titration curve itself is something that looks like this. All right, and these shapes are actually very, very common for strong base, strong acid titrations. If I actually had in this case we had a strong base, strong acid titration, but if we had a strong acid, strong base titration, then basically we would get a curve that would sort of be a reflection of that. For a strong acid, strong base titration, we'd get something that looks more or less like this. Where again, the key features to note is again how quickly this region of the curve shows a change in pH. All right, that actually helps us out in terms of selecting indicators, and it also helps us to characterize different titration curves as being strong acid, strong base, or weak acid, weak base, and so on. And so go ahead and work on the follow-up assignment for this particular tutorial, and we'll discuss this in class. If there are any questions, by all means email or bring up the questions in class. All right, have a good night.